Welcome to the class. Dear students, today we are going to discuss on achiral compounds and what are elements of symmetry. So first we will discuss on achiral compounds. We will see examples of achiral compounds, and then we will look into the conditions of being for a compound to be achiral. So the condition is it should have at least one element of symmetry. So that is what we are going to see in this class. So let us start. Achiral compounds. Achiral compounds are symmetrical compounds which have a superimposable mirror image. By symmetrical, what I mean is that it can be divided into two equal halves, the two halves being mirror images of each other. You can see this is cyclopropane. It can be divided into two equal halves. The two halves are mirror image. This is cyclobutane. The two halves are mirror image. Similarly, this is cyclohexane. How this is a mirror image of this? This is ethane. So these are all symmetrical compounds because they can be divided into two equal halves by a imaginary plane, right? And if you are bringing a mirror, if you are drawing a mirror image, it will have a superimposable mirror image. Am I right? Yes, it will have a mirror image that will be superimposable. So that is the first, that is the thing of, that is what is called as an achiral compound. Number one, it should be symmetrical. That is, the molecule should be divided into two equal halves by an imaginary plane, the two halves being mirror images of each other. And the second condition is that if you are bringing a mirror before it, then a superimposable image would be formed. So these are the two conditions first for achiral compound. Now, achiral compounds, all the compounds that are having an achiral carbon atom, they are achiral compounds. Okay, and a chiral carbon atom, there are compounds that are having chiral carbon atom. A chiral carbon atom, as you know, it is attached to four different substituents. Okay, I'm writing it here as A. Okay, so this can be CH3, H, Cl, F, right? Four different substituents. Even if this one is X, then this carbon atom becomes achiral. So it is required for a chiral carbon atom, that is chiral carbon atom should be attached to four different substituents, right? So there are some chiral carbon atoms. There are some compounds that contain chiral carbon atoms, but they are still achiral compounds. Okay, so let us see the second point more clearly. All compounds that contain a chiral carbon atom, they are achiral compounds. See, this is achiral, this is achiral, this is achiral carbon, this is achiral carbon, this is this. All these are achiral carbon because they are attached to same kind of substituents. Right, so they are all achiral compounds. Why? Because they can be divided into two equal halves. They have symmetry. Yeah, they are symmetrical and they have a superimposable mirror image. So what cannot be divided into two equal halves is a chiral compound like this. But in chiral compound also there are some compounds that are overall achiral. We will see the example. Okay, we will see the example to better understand it. So I'm going to draw a chiral carbon atom. So this is your mesotartaric acid. Okay. This carbon atom is chiral carbon atom because it is attached to four different substituents on the four sides, and this carbon also is a chiral carbon atom. It is also attached to four different substituents on both sides, on all the four sides. But the issue is that it can be divided into two equal halves by this plane. The first half is the mirror image of the second half. So as it can be divided into two equal halves, the first half being the mirror image of the second half, the compound is achiral. Overall, it is symmetric compound. Am I right? So symmetric compounds are called as achiral compounds. symmetric compound is called as achiral compound. So there are some compounds that contain more than one chiral carbon atom. This one, it has more than one chiral carbon atom, but even though they have more than one chiral carbon atom, they are still achiral because they have a plane that can divide it into two equal half. So that makes the molecule overall a symmetric molecule, and therefore such compounds are achiral. Overall they are achiral. So such compounds that have more than one chiral atom but still they are achiral, these compounds are called as meso compounds. They are called as meso compounds. Okay, so meso compounds are those compounds that have got more than one chiral carbon atom, but still they are not chiral as a molecule. They are achiral. Fine. Okay. Now, the third point for achiral carbon atom, the third point for an for this achiral compound is that they have no optical activity. There is no optical activity. We know what is optical activity. The activity that is exhibited on plane of polarized light. So some compounds, they can shift the plane of polarized light to right, and some can shift the plane of polarized light to left. So that activity is called as the optical activity. Okay, so now they don't show any kind of optical activity, which achiral compounds. So achiral compounds don't show any kind of optical activity. So that includes compounds that have got achiral carbon atoms, and that also includes your compounds that have got chiral carbon atoms but still overall they are achiral. That is, this includes meso compounds also. Okay, overall they don't show any optical isomerism. One reason is, see, for achiral it is symmetric, right? It is a symmetric molecule. So if you are bringing a mirror image, okay, if you are drawing a mirror image, you get the same image, a same superimposable mirror image. So there is no isomer, correct? It's not, there is no isomer possible because you get the same image. It's not it's superimposable. Okay, so there is no isomer that is possible. So there is no kind of optical isomer that is possible, or there is no kind of enantiomer that is possible, and there is no question of it showing optical activity because there is no kind of isomer that is possible. So that is why, because it is a symmetric molecule, achiral molecules, achiral compounds, they don't show any kind of isomerism, optical isomerism, nor do they show any kind of enantiomerism, that is the same thing as optical isomerism. So they don't show any optical activity also, because they don't show any kind of isomerism, because they are superimposable mirror image. They form mirror image that are superimposable. And why they form superimposable mirror image? It is because they are symmetric in nature. Fine. Or overall symmetric, as in case we have seen of meso compounds, right? So these are the four main important things. So we have discussed that achiral compounds, they are symmetric, they form superimposable mirror image, they are all of the achiral compounds, all of the compounds that have achiral carbon atoms, they are achiral molecules, and there are some that have chiral carbon atoms but they are still overall achiral, and these are called as meso compounds. And be it meso compound or be it achiral compound that have a chiral carbon atom, both are optically inactive. Okay, now let us see one more point. For a compound to be achiral, it should have one of the elements of symmetry, at least one. It can have two, but at least one element of symmetry it should have. What are the elements of symmetry? The first element of symmetry is plane of symmetry. Plane of symmetry. Let us understand plane of symmetry. So we will see whether these kinds of symmetry, these kinds of planes of symmetry or center of symmetry, are they able to divide the molecule into two equal half or not? Okay, we will see this and then we can judge. It is to know that whether a molecule is achiral or not. We are using these elements of symmetry to know whether our molecule in hand, it is achiral or chiral. Okay, so we will see this plane of symmetry. So I take this example, we have already seen it. Yes, already we have seen all these examples. I take a different example here. 1,2-dibromoethane. Okay, now I am taking butene. 1,2-dichlorobutene. Fine. Okay, and I can take this example also. I will take that later. Okay, all these are you can say achiral carbon atoms. Now let us see whether they are having plane of symmetry or not. Okay, a plane of symmetry is a plane. It is a plane. It's an imaginary plane that can dissect the molecule into two equal halves, the two halves being mirror images of each other. So it is a plane, imaginary plane. Okay, this is a plane, imaginary plane. It can dissect the molecule into two equal halves. Okay, the two halves are mirror image of each other. So if it is so, if it can divide it into two equal halves, then it means that the molecule is achiral. So this one is achiral. This one is achiral because the plane of symmetry can divide it into two equal halves. So it is achiral. So we are using this element of symmetry to know whether it is achiral or chiral. So here we can divide it like this. It can be vertical or horizontal. Okay, the plane can be vertical or horizontal. Here we have got a horizontal plane that can divide it into two equal halves. So this is also achiral. Now look at this. This is 1,2-dibromoethane. Look at this. This is butene, right? So dichlorobutene, as we are seeing here. Now we can divide it like this. Fine. So this is also achiral. Correct. Now as we will see the plane of symmetry in meso compound also. One more example I will give to you. Mesotartaric acid. This is mesotartaric acid. Why it is called as meso? Because it has got chiral carbon atom, but it is still achiral. That is why it is called as meso. Why it is achiral? Because you can draw a plane that can divide it into, that can bisect it into two equal halves. The one half is the mirror image of the other half. So here it is having a plane of symmetry, right? So it is a mesotartaric acid. Mesotartaric acid is an image acid. Now if you are seeing you want to see whether it forms a superimposable mirror image or not. So let us see. If I am bringing a mirror like this, I get an image like this. Right? So is it superimposable or not? Superimposable means you have to keep this molecule like this. Okay, that is superimposable. Is this superimposable on each other or non-superimposable? It is superimposable on each other. Why I am saying it superimposable? At first glance it may seem it is non-superimposable. If you are keeping this one over this OH would come here, this OH would come here, this H would come here, this H would come here. It would, first glance it would seem that it is non-superimposable. But the molecule, this molecule is not rigid. Okay, it rotates like this. Okay, the way I am rotating, just observe me. The molecule can rotate in this manner. Okay, so it is not fixed. Fine. So in this way, if the molecule is rotating, it would become superimposable. If this molecule, it goes for a rotation, a 180-degree rotation, it would become the same like this, right? So they are actually superimposable mirror image of each other. So there is no optical isomer for mesotartaric acid. There is no enantiomer possible for mesotartaric acid, and because there is no optical isomer, because there is no enantiomer possible, it would never show any kind of optical activity also. Okay, it all started from what? From the plane of symmetry, right? It all started from the plane of symmetry, right? So the plane of symmetry is the first test to know whether it will form a superimposable mirror image or not. There is a plane of symmetry, that means that a superimposable mirror image is formed. That means that there is no optical isomer for this compound. That only means that there will be no optical activity also. So this is an example of mesotartaric acid. Okay, see, mesotartaric acid, another isomer I will draw. Okay, another isomer I will draw, and I will show you in that how optical isomerism is possible. Okay. I am rubbing this mesotartaric acid from here, all these things which I don't need. Okay, now another isomer I will draw here. I will remove this OH and just OH and H. This is another isomer of tartaric acid. It's not mesotartaric acid. This is another isomer of tartaric acid. If I draw a line like this, if I put a plane like this here, will I be able to divide it into two equal half which are mirror image of each other? No. I would be able to divide into two equal half, but that would not be mirror image, because here the OH is here, H is here, H is here, OH is here. So for this there is no plane of symmetry. A plane of symmetry for this isomer is not possible. Correct? So if you are drawing a mirror image, so what we will get, let us see. This H would come here, OH would come here, H, OH, COOH, COOH. Now look at this. This is the optical isomer which is possible. Okay, you can rotate it like this 180 degree. I have shown you how I rotated. So you can rotate it like this. Even though if you rotate it 180 degree, it is non-superimposable. Right? So they are non-superimposable mirror image of each other. They are, better than using they exist as these images. They actually exist as non-superimposable mirror images of each other. In nature they exist as these molecules, and the phenomena of this existence is referred to as enantiomerism or optical isomerism. Enantiomerism. The pair is called as enantiomer because they are non-superimposable mirror image. Enantiomers are non-super mirror images of each other. Right? Isomers that are non-superimposable mirror image of each other. Now they exist as enantiomers. They exhibit optical activity. One of it may rotate the PPL towards the right, and one of it may rotate the PPL towards the left. I don't know which. We have to see it in polarimeter, which rotates it to the right and which rotates it to the left. The one of it, which rotates to the right, is a plus isomer, and the left rotating isomer is the minus isomer. So we are seeing that it is because there is no plane of symmetry in this isomer. It is optically active. It shows non-superimposable mirror image only because it doesn't have any plane of symmetry. So if it had plane of symmetry, it would have not shown this kind of optical isomerism. Now let us see the second test, the second method to know whether a compound is chiral or achiral. The second is center of symmetry. Center of symmetry. Let us see what it is. Let me first draw and then we will see what it is. Okay. Pardon me. So this is one. This is 1, position 2. This is 3, and this is 4. So this is 2,4-dimethyl cyclobutane cyclobutane, 1,3-dicarboxylic acid, 1,3-dicarboxylic acid. Now you can see that center of symmetry. What is center of symmetry? Center of the symmetry is the imaginary center. It's an imaginary point in the center of the molecule. It is an imaginary point in the center of the molecule from which if lines are drawn, this is here CH3 and here it is H, from which if lines are drawn on opposite ends, okay, from which if the lines are drawn on opposite ends at equal distances, it would meet, that line would meet similar groups. That line would meet similar groups. Let me repeat. See, right? Right? So what I mean to say here is that it is an imaginary point in the center of the molecule. This is very let me draw it little more bigger so that we can understand it. Okay, this is cyclobutane and here we are having 4 groups. Okay, you just draw here our CH3. You draw CH3 here, put it in transposition, everything. Here you draw COH, here you draw COH, here you can draw H, put it in transposition. Now it is an imaginary point in the center of the molecule from which if lines are drawn on opposite ends, it would meet similar groups at equal distances. Okay, so you can see here we are drawing line from that center of molecule on opposite ends and how it meets similar groups at opposite ends. So this is a molecule with a center of symmetry, and because it is having a center of symmetry, this is an achiral compound. It is a achiral compound. I hope you understood it. It's the point in the center of the molecule, imaginary point, from which if lines are drawn towards the opposite ends, okay, towards opposite ends, it would meet similar groups at equal distances. Okay, if the molecule has it, it is called as center of symmetry, that the molecule is said to have center of symmetry and that the molecule is said to be achiral. Let us now see another example of achiral compound. Another example of achiral compound. Look at this compound. This is trans dimethyl piperazine. Okay, trans, you have to draw trans, put CH3 here, put CH3 here, H here and H here. Now what is the center of symmetry? It is the imaginary point in the center of the molecule, okay, from which if lines are drawn on opposite ends at equal distances, it would make similar groups. See, we have drawn a line from the center on opposite ends and how it meets similar groups we have seen. H and H, correct, and CH3 and CH3. So this molecule, that is trans dimethyl piperazine, this molecule is said to have a center of symmetry and this molecule is achiral. That means it is a superimposable mirror image will be formed. If you are bringing a mirror, a superimposable mirror image will be formed. No enantiomer will be possible. It would not display any kind of optical activity because there is no kind of optical isomerism. So trans dimethyl your piperazine is having a center of symmetry. It is optically inactive, okay, and it is a achiral compound. Now let us see a contradictory example. It doesn't have center of symmetry. We have seen trans. Now we will see its cis isomer. Same compound you draw, and make the cis isomer. This is the same thing. Now we are making cis isomer. Put CH3 here this time, and H here. Now this is the center of the molecule, imaginary point from the center of the molecule, from which if lines are drawn on opposite ends, then it should meet similar groups. Is it meeting similar groups? No. Is this one meeting similar group? No. So this compound, that is the cis isomer, cis dimethyl piperazine, it is chiral. Piperazine, it is a chiral compound. Okay, it is overall chiral compound because it does not have any plane, any center of symmetry. There is no center of symmetry here. Whereas trans dimethyl piperazine, the compound that we drew before this, the trans one, it had a center of symmetry. But a cis isomer, cis dimethyl piperazine, it doesn't have any kind of center of symmetry because it's not meeting similar groups on opposite ends. So this compound is not a chiral compound. This is a chiral compound. This is a asymmetric compound. It will show optical isomerism. If you are bringing a mirror, it can exist as it will exist as a pair. It will exist as enantiomer, and it will show optical activity. So because it is not having any kind of center of symmetry, it will exhibit optical activity. So the cis dimethyl piperazine, it doesn't have center of symmetry. It will display optical activity. It will display enantiomerism also. Okay, so it should have at least one, right? That is what we have seen. So it is not having any center of symmetry, nor it is having plane of symmetry. Now let us see the third the third criteria to know whether it is chiral or achiral. The third is alternating axis of symmetry. Alternating axis of symmetry. So let us see what it is. As we were discussing the alternating axis of symmetry, so a molecule is said to have an alternative axis of symmetry if the molecule it can be rotated at predetermined angles of rotation, and it has to be rotated overall at 360 degree. Okay, so if by rotating at predetermined angle of rotation, if you will get a structure. Okay, if you are taking a mirror image of that structure, okay, if you are putting a plane and if you are mirroring that image, and if that image is identical to original structure, then your compound is said to have an alternative axis of symmetry. That is, an alternative axis of symmetry, a molecule is said to have an alternative axis of symmetry if the molecule it can be rotated at predetermined angle of rotation till it is rotated overall to an angle of 360 degree, and after each predetermined angle of rotation it is reflected across a plane. It is reflected across a plane perpendicular to its axis, and if the image formed is a image that is identical to the original structure of the molecule, then that compound is said to have an alternative axis of symmetry. So this is the angle by which we are rotating the molecule. This is the angle by which we are rotating the molecule. So we have to rotate at 360 degrees Celsius. That means this, it will come this like this. If it comes like this, it is a 90-degree rotation. So it has to be turned like this 4 times. Okay, this 90-degree, it has to be 4 times to make it 360 degree. When it is 360 degree, this position will come back, right? The CH3, this carbon will come back at its this position, initial position. So it is 4 times that you do like this, right? So we have determined, we have set, there is the predetermined angle of rotation. We have set that angle of rotation to be 90 degree. Okay, you can make it 60 degree or 180 degree depending upon your molecule. So here my molecule is having this kind of square kind of shape, so I have decided it to be 90 degree. Now I rotated by 90 degree till I reach 360 degree. That is, till this initial carbon is at this position. So whenever I rotated to 90 degree, so this is the first type of rotation. So when I did it for the first time, I got a structure like this. Okay, this CH3 has come here, correct? This H has come here, right? This CH3 has come here, am I right? This CH3 has come here, right? This H has come here, fine, and this H and CH3 it has come here. So it is pakka 90-degree rotation right now. So after I get this structure, I just reflect it across the plane, just perpendicular to the axis. I reflect it across the plane perpendicular to the axis. So when I reflect it across the plane perpendicular to the axis, I get this kind of structure, which is mirror image of this. You can see how it is mirror image. This H, it is here, right? This CH3 it comes here. This CH3 it comes here. This H it comes here. This H it comes here, right? And this CH3 comes here. So whatever is in the top, it goes to the bottom, and whatever is in the bottom, it goes to top. Is it right? That is the mirror image, right? So this is the bottom, right? It is here, right? And this is the top, it is here, correct? So I get a mirror image like this. Now this mirror image is just identical to the initial original structure of the molecule. So if it is so, at predetermined angle of rotation, if it is so, then my molecule is said to have alternative axis of symmetry, and because it is having alternative axis of symmetry, the molecule is achiral. Okay, that means it will not show any kind of optical isomerism, nor it will show any kind of optical activity. This is what is it? Tetramethyl cyclobutane, correct? This is 1 2 3 4 tetramethyl cyclobutane. So I am getting this thing. I am going to give you the definition one more time. Alternative axis of symmetry, a molecule is said to have alternative axis of symmetry if it is rotated at predetermined angle of rotation till the whole molecule is rotated to an angle of 360 degree. At each predetermined, after each predetermined rotation, a mirror image is drawn across the plane perpendicular to the axis. If that mirror image is identical to the original structure of the molecule, then that molecule is said to have an alternative axis of symmetry, and therefore the molecule is said to be achiral. So this is what is alternative axis of symmetry. So there is a formula for alternating axis of symmetry, which is as n-fold alternative axis of symmetry. So here we have to n-fold alternative axis of symmetry. So here we have to rotate it by 360 degree, right? And what is the predetermined angle of rotation? 90 degree. So you are seeing that there are 4-fold, the answer would be 4, correct? So there is 4-fold alternative axis of symmetry. This molecule is said to have 4-fold alternative axis of symmetry, right? Right? So it will be denoted as S4. 4-fold alternative axis of symmetry this molecule is said to have, okay, and it will be denoted by S4. However, for our purpose, we need to only know that the molecule is chiral or achiral. So it is achiral because it is having alternative axis of symmetry. As I already said, to know whether it is having an alternative axis of symmetry, you have to rotate the molecule at predetermined angle of rotation till the whole molecule is rotated to 360 degree. After each rotation, predetermined rotation of the molecule, you have to mirror that molecule across the plane, correct, perpendicular to the axis. If you get a structure that is identical to the original structure of the molecule, then that molecule is said to have alternative axis of symmetry. Then that molecule is achiral in nature. There will be no optical isomer formed, nor there will be any enantiomer. Actually, you can see, no need to find out your alternative axis of symmetry. This actually has a plane of symmetry. That's so simple, right? It has a plane of symmetry. You can divide the molecule like this, or if you want, you can divide it like this, or you can divide it like this, correct? And it is also having a center of symmetry, right? It's not having a center of symmetry, but there is a plane of symmetry. You can divide it like this, and you can divide it like this, and you can divide it like this also, right? It is also having a plane of symmetry. It is also having an alternative axis of symmetry. Therefore, this molecule is achiral. Dear students, I hope you have understood the class. If you have liked the class and if it was useful for you, please do not forget to subscribe the channel and to like and share it with your friends. Thank you very much.